Okay. Do you hear me now? Thanks. Mr. Chairman, ladies and gentlemen, colleagues, I will present the difference in the physical mechanisms of both cold nuclear fusion and thermonuclear fusion, because both of them are fusion reactions. However, the outcomes are different, and they are based on different mechanisms. I will show today my point of view of this difference without comparison with other approaches, especially theoretical approaches. I'm not going to criticize other theoretical approaches. My theoretical approach is quite different. However, I'm ready to discuss the difference in the approaches. Okay? The experimental results are published in these actually 3 papers in the peer review journals. Generally speaking, 1 and 2 accommodate the results which were already presented in Szczecin and in Strasbourg. They are published experimental results. Now, I would like to show a video clip regarding cold nuclear fusion reaction during the pulsing injection of deuterium gas. You can see the glow. It comes because of the brightness of the wire. The temperature of the wire now is about 1040 degrees Celsius. No plasma is used in the experiments. There is energy release now. This actually video clip was taken a few days before I submit the presentation to the conference now. So it is actually some kind of paired results showing energy released based on temperature release. That's it. Okay, now, again, bare results corresponding to the same experiment. You can see 2 experiments, one actually 2 pulses, 2 pulses of deuterium injection in the chamber, the other one 5 pulses. In fact, the red line of the represents which is above the red graph, by the way, which is above the blue line, horizontal line, represents exactly the temperature increase due to interaction of deuterium gas by itself inside of the constant wire. Generally speaking, we can see here decrease in the beginning of the injection of the temperature. It happens because deuterium gas having room temperature is cooling the specimen initially. After that, actually, the reaction begins and we have temperature increase in all of these experiments. Last 2 slides were actually bare results. In the fall, actually, was published this paper giving actually results, previously received results. It is actually initial temperature of the wiring. It is actually final temperature of the wire. We can see approximately increase with 400 degrees Celsius, the temperature, for the time less than 30 seconds. Here we see the release power in watts. Here we can see the ratio between 43 different experiments between the output power and input power. Here we see the density of the release power in watts per gram of the constant on wire. we can see strong correlation with energy yield with the initial temperature. If we increase the initial temperature, energy yield increases. Generally speaking, it is actually confirmation that we have fusion reaction because of helium release. Helium release here, it is for two different experiments, having different in the temperatures about 8 degrees Celsius. And we can see strong correlation between energy release and release of helium-3. Again, energy release of helium-3 and energy release for the air temperature. The same we have about release of helium-4 versus the energy. This is release of helium-4, this is versus energy. So now, this table compares achievements at my lab and achievements compared with achievements of national ignition facilities of Lawrence Livermore National Laboratory. It's actually the ratio between output power and input power here. Here is their ratio. Here is the operational temperature in my lab. Here we have actually significant more. The fuel is deuterium gas interacting inside of the structure of a constant wire. They use deuterium-tritium gas. Tritium is radioactive. Released radiation and radioactive waste. No, in both cases in my experiments. Here we don't have reported data. Just I would like to open a bracket on the basis of the achievements, experimental achievements. A company was established. I am CTO of this company. And the feasible goals of the company is development of 3 different energy sources. One 20 kilowatt, the other one between 10 megawatt electrical energy on the output, and the other one is development of 300 megawatt modular reactor using this actually approach. I'm going to close the bracket now. Mechanism of thermonuclear fusion reaction. Generally speaking, we have electrical repulsion between both interacting nuclei. In order to get thermonuclear fusion reaction, the initial value of the approaching deuteron or triton to the initial deuteron or triton nucleus must be significant, like in order actually to overcome the gamma potential and the potential energy and the quantum tunneling to occur here. Okay. Generally speaking, we have energy release. However, we have significant deacceleration of the colliding nuclei giving gamma rays release. And also we have neutron release in the range of mega electron volts. Again, I'm going to present now my point of view regarding the mechanism of cold nuclear fusion reaction. This is theoretical point of view. Electron critical non-zone effective mass is introduced. It is criterion about localization of the electrons. Generally speaking, this non-zone effective mass is different than the effective mass connected with electron effective mass connected to the Brillouin zones, simply because actually when we have lattice vibrations by themselves break the crystal symmetry, and the approach about electron effective mass connected with Brillouin, which is emanation from the Brillouin zones, does not work. It is not correct. Generally speaking, with lattice vibrations we can achieve, it is actually a little bit more complicated formula, obtained by actually second quantization quantum mechanics, something like that, based on vibrations. And it is determined to be the critical non-zone effective mass where we can expect cold nuclear fusion to occur, 153 times greater than M0. It is M0, it's mass in rest. However, it is actually again, criterion about localization of the electrons. Here we have lattice vibrations, localized electrons, deuterons propagating inside of the lattice. Generally speaking, it can be considered to be nickel cluster, crystal lattice of nickel clusters in the constant arm. It's actually distribution of the potential here. We see here the potential, the localized electrons. We have minimum of the potential here. We have actually propagating deuterons. Generally speaking, the theoretically determined temperature, pure theoretical determination of the temperature, giving electron effective mass necessary is 482 degrees Celsius. Experimentally observed in my experiments is about 500 degrees Celsius. 18 degrees Celsius is the difference between purely determined theoretical mass. So now, mechanism of cold nuclear fusion, continuous molecular, deuterium, electron, heavy electron, this structure in solids. Generally speaking, it is similar to the muonic molecule approach. We have actually two deuterons here and two heavy electrons forming this structure. Generally speaking, these two electrons initially belong to nickel atoms in their vibration. We must have exact overlap between S molecules of nickel to neighboring nickel atoms in order which happens approximately for about 500 degrees Celsius. Delta X, it means replacement of the atoms from their initial positions are about 0.162 angstroms. And for this actually, we can achieve the electron effective mass, non-zone effective mass, this amount, 153 times greater than electron effective mass in rest. In this case, the distance between two deuterons is this amount, which is comparable with the distance between the interacting nuclei in the muonic molecule. Now, distance between two 4s electrons of two neighboring atoms, this distance here corresponds to hydrogen-like molecule. However, if this distance becomes less, we have actually a region where two localized electrons attract the corresponding deuterons. The question is, okay, how can we achieve this actual value here, potential value here? The answer is connected with the magnetic interaction between two interacting electrons, additionally to their belonging to the 4s orbitals of the neighboring nickel atoms. So here is another way. Here we have hydrogen-like molecule. Here we have electron couple attracting. There is a reasonable question. How the electrons can go from here to here? How they can overcome this actually high potential barrier? Generally speaking, by quantum tunneling. As a matter of fact, the quantum tunneling rate is a little bit less than 40%, 40. Okay. The distance between these two electrons will become certain in order actually the corresponding deuterons to approach the electron cloud on this distance, and this distance corresponds to the Compton wavelength. Synthesis of helium-3. Two deuterons plus we must have odd number of heavy screening electrons in fusion in the fusion well. It means well where the electrons are localized. Deuteron plus heavy electron, which is not paired, gives actually, in fact, helium-3 plus 2 electron plus proton plus energy. Generally speaking, I'm going to mention the mechanism how it happens later. Generally speaking, we have actually here stimulated conversion by the heavy electron of a neutron, converting the neutron into proton, and we are going to have this initial electron plus the electron, heavy electron, which has been created due to the conversion of neutron into the proton. Here we have, if we have even heavy screening electrons in the fusion well, which means they will pair, we have actually this kind of reaction. In this case we have helium-4, plus these two heavy electrons, plus energy release. Generally speaking, how we can have conversion? Here, I used actually modification of Dirac relativistic equation, and I introduced actually charge factorized mass, which parameter unifies the mass of the quarks and the charge of the quarks inside of nuclei. If we have proton plus one heavy electron, it gives neutron, and we have the corresponding change of the charge factorized mass. If we have actually interaction between neutron and heavy electron, we have actually proton, creation of proton, and we have another change of parameter mass, charge factorized mass. Now, the interesting thing here is that this purely determined parameter corresponds approximately to the mass of the electron in rest. We can see this kind of correspondence. I can answer any questions if there are. The matter about radiation release. Generally speaking, if a deuteron incorporated in the structure of nickel clusters can interact by itself with heavy electron, and it depends on the electron spin, we are going to get two neutrons and transition from low to high nuclear energy state. In this case, we may expect neutron release. However, in my experiments, no neutron release was observed, which means that, okay, this question is quite open for further determination, because I consider that, in fact, we may have electron release. However, there is no reason to consider that we have high energy electrons. Most probably we have electrons having energy, low energy, and we may have cold or ultra cold neutrons. Regarding gamma rays release, in fact, actually, there is no reason to consider gamma ray release, simply because the initial kinetic energies of the interacting deuterons are very low. And in fact, we don't have the acceleration. So there is no way to get actually gamma release. Generally speaking, 10 days ago, and much time before my experiments, this actually matter was treated in the same way in this actually literature source. Thank you very much for your attention. I will be happy to answer to all of your questions regarding the presentation, except the questions regarding the company. If you want to ask me the questions after the session, you are welcome to ask me. Thank you.
Thank you, Dimiter. So, questions? Yeah, Conrad.
Thank you very much for your presentation. My question, I have two questions. First one, have you checked your experimental results with hydrogen, not deuterium, but light hydrogen? Because this is a method to distinguish between nuclear and chemical effects you have. Okay? Okay.
I checked, generally speaking, we have energy yield there. However, it is difficult to be determined what is the origin of the energy yield. Because actually, in my experience with deuterium, part of the energy yield comes from has actually chemical origin coming from burning of deuterium gas in the atmosphere of parasitic injected oxygen in the chamber. We cannot ignore this one. However, this rate is about 600 times less than the total released energy. The same energy has during the release of hydrogen. The same. The total energy of the hydrogen is comparable with actually the energy release because of burning of hydrogen. It means in both sides, burnings give approximately the same energy. But in case of deuterium gas, we have actually 600 times greater release energy than comparison with hydrogen. Thank you.
Yeah, it depends on that how much hydrogen and oxygen you assume you have in the chamber, okay? Then you can compare it maybe properly. Another question is, you are speaking about heavy electrons, but you know, the electron screening, this, in effect, this contributing by many electrons, this long-range effective interaction, this is a kind of collective effect of many, many electrons. There are not two or one electron separately, because it's not enough to explain the screening energies we measure. So this, as I said, many electrons, not one electron, of course. You know. So, but nevertheless, the screening should be proportional to the square root of effective electron mass. And but once again, there is not you cannot. I think at least, you know, in the frame of the localized heavy electrons, just between two different deuterons or protons, whatever you want to say. Okay, so this because the screening, this very general effect can be studied in atomic physics, in optics, everywhere. And it is just a bending curvature of the conduction band. So it is something what we can measure using different optical methods, for instance. Yeah.
Okay, I'm going to answer this question this way. Okay, we have actually indeed collective behavior. But the question is, okay, how many are these actually electrons in the electron cloud? How many? Because actually, let's say in the crystal lattices of nickel clusters, let me put the things in this way, we should not expect too many electrons. We may expect actually, let's say, 1 electron, 2 electrons, 3 electrons, 4 electrons. And generally speaking, it happens because of the contribution of the electrons coming from the copper clusters in the constant term. That's why. How many there are? So now, it is collective behavior, but as I mentioned here in my presentation, it depends, the reaction depends on how many electrons we have in the well. If they are odd electrons, we have helium-3. If they are even, it means they are paired, we have helium-4. Generally speaking, it is the matter. Collective behavior, yes, but how many are they? Especially between doing screening, because the screening must be done between two nuclei, two deuterons in this case. It is the matter.
There's another point. If you use mass spectroscopy, it is very difficult to distinguish between two deuterons or helium atom, you know, so it is very difficult to do it. Even helium-3, you can have deuteron and proton, and then you have mass 3 as well. So it is very difficult, you know, to distinguish between different atoms there, you know. So, but we can discuss it maybe later on.
Of course, you see now, Konrad, I agree that actually it is subject to further investigation regarding these things. But at least it you required a little bit more complicated experimental circuit, because actually we must perform these measurements during the synthesis, during actually this increase of the temperature, energy release. It is the matter. It means it must be done in situ at certain time. These are the things. Okay, thank you for the questions.
One more question.
Yes,
yeah, one question about you showed your let's say, reaction equation, D plus D plus two heavy electrons, and to show can I show this equation again? Because
Okay, I'm going to
Yeah.
could you please put again the presentation?
oh, sorry, it's already
Okay.
because
I'm going to show
because
it.
to do that you need a neutrino right side in that.
Oh, this one here.
Yeah.
Okay, yes.
That's very funny because how can I get a proton?
No, I'm going to tell you how. Generally speaking, a heavy electron, this heavy electron here, interacts with one, it is actually extra heavy electron, which is not paired. And it interacts due to its,
Yeah,
its spin
but
with
anyhow-
one of the deuterons, converting one of the deuterons into two protons. They
Yeah,
can
then the
convert it.
lepton number does not reserve. I mean, you need a neutrino right side of the equation, and then if you have a neutrino, almost all the energy gone
Okay,
by
regarding
neutrino.
neutrino, I agree
Yeah,
with you.
maybe we will discuss later.
No, perhaps we should actually think about the existence of neutron. That's why actually here I put energy. This energy here accommodates maybe some other particle, neutrino, or something like that. But this is actually the equation, and we have actually, in fact, actually stimulated conversion of nuclei. It could be either proton or neutron into another state.
But from proton to neutron.
Is possible.
Well, but with neutrino. Without neutrino, it's impossible.
Could be, but yes, could be, but actually it is connected with the localization of the heavy electron.
You could have an antineutrino coming on the left side of the equation, and then you would have kinetic energy coming out on the right, and it would be Parkhomov's theory of how it occurs.
Okay.
So you still have kinetic energy on the right-hand side, you don't lose it to the neutrino.
Well, that's why I didn't present neutrino, because actually it is not clear. Is there a neutrino or not? Maybe yes, because generally speaking, maybe yes, maybe not. Because actually the reaction is different here. Everything is based on conversion of interaction of heavy electron. It is some kind of lasers. In lasers we have stimulated optical radiation because of photons. Here we have similar things. Simply a heavy electron stimulates conversion of neutron into proton or proton into neutron. These are the things.
Dimiter, are you aware of Parkhomov's over 1,000 degrees producing two relic-type cold ultra-low momentum neutrino pairs, antineutrino, neutrino, and then the antineutrino would feed this reaction?
Generally speaking, it is subject of initial investigation, and I cannot say now yes, but I cannot say now no.
Okay, thank you.
These are the things.
Okay, thank you, Dimiter. So let's thank again